school level mathematics. So this is the definition of a group. And in general, A plus B is not necessarily equal to B plus A. But if it is, if A plus B is AP in X, then the group is commutative. So if we start taking some examples of groups. So one of the first example that with uh, which we uh, think of in case of groups is this example of modulus. So if we take X as, let us say, Z5, which is, or I should write, I think this is Z mod 5Z. The meaning of this is just the set of all numbers which are less than 5. In general, we could have taken X equal to Z mod NZ also, which is the set of all elements up till n minus 1. And if we define the plus operation as addition modulo basically I have X as this set, and we can have addition modulo. Then we can verify that X plus is a group. In fact, it is a commutative group. So how do we verify? We just have to verify the conditions of the group. So the first condition is if we take two numbers A plus B, which is equal to A plus B, so addition modulo n. So this number, this is in X, this is in X, and this number is also in X. So the first condition is satisfied. The second condition is existence of an identity element. So the identity element is 0. Because A plus 0 mod n is the same as 0 plus A mod n, which is equal to A. And the third is existence of inverse. So for any A in X, if we take the element n minus A, then this is also in x, because x starts with a can be 0, 1. So if x is 0, uh, we will take the element as 0 itself. But for all a not equal to 0 in x, we can consider this in which n must be and a plus n minus a is equal to 0 modulo n. So basically n minus a is the inverse, is the inverse a in x. So all the condition group is satisfied. Hence we have verified that this example is a group. Next example is that of, we can take the example of x as z mod nz, where n is prime and the so z mod nz, it contain other than 0. So x is basically 1, 2 till n. And the operation is multiplication mod n. So basically when you take two elements, a plus b is defined as av mod n. So in general it is better that if we write n as p, because it's an indicator of a prime number. So let us try to verify that it's a group or not. So clearly the first condition is a plus b. This is in x, this is in x. If we take the product and take again mod p. So since p is a prime number, and a and b are values which are less than p, so their product cannot have p as a factor. If we take if we take any arbitrary element, A, then we have to multiply it with some number x such that ax is equal to 1 mod b. So in general, we should be able to write that ax should be equal to 3 times k plus 1, where k here. Another way of saying this is ax minus 1. So x is basically x is equal to pk plus 1 divided by a. So this is a property of this group, is that such an element x exists such that if you take the product of a with x, it gives it gives the value which is equal to 1. So the inverse of every element also exists. We can construct some examples like 1, 2, 3, 4, and inverse of 1 is 1. Inverse of 2 is relative module of 5. Inverse of 2 is 3. Inverse of 3 is 2. Inverse of 4 is. So we can verify that in general we will always be able to find a number x between 1 to n minus 1, 1 to p minus 1, such that the product of those two numbers gives a value which is equal to p times k plus 1. One can be a bit more formal about this proof and actually verify the value of x here. For what we basically want to show that some k exists such that when multiplied with x, it gives a modulo which is 1. These are some examples of groups, and maybe in the next class I will do a bit of number theoretic this proof. Maybe I will do in the next class. So these were some examples of groups, and groups is a huge topic in abstract algebra with many applications and uh, application to many fields, and not not only in mathematics but also in other disciplines like physics and all. So groups are also used to capture the notion of symmetries in physics. So there is a concept of uh, generator of a group, which is an element G in G, which is equal to x comma plus, such that every element A can be written as G plus G k times for some integer k. So this is the concept of a generator, and we can verify that every group can be generated by a particular number. So for example, if we take the first example, then which is the first example, which is this example. In this example, what will be the generator? Clearly the generator is 1, because any number can be written as an addition of ones. In the second example, what is a generator? So we have this case, which is 1 to p minus 1, and we are doing modulo p. What is the generator? So basically, we should be able to say that any number A should be written when we should be able to write it as g power k mod p. So g power k simply means multiplying gk times. So if we take the example simply 1, 2, 3, 4, so obviously 1, if we consider um, 2 to be the generator, so 2 power 4 is 1, 2 power 1 is 2, 2 power 3 is 3, and 2 power 2 is 2. 2 power 2 is 4. So we have verified that for the group 1, 2, 3, 4, and the operation is multiplication mod 5, we have verified that 2 is the generator. In general, we have to check whether for every group, is it true that there is always a generator? So this is the question that we need to answer. But for these two groups, obviously we could find a generator, but in general, is it true that every every group has this property that it can be generated by one single element? So the answer to this question is no. In general, it is not true that every group is generated by a particular generator, but if such generator exists, then it is called a cyclic group. And we will discuss the proof of this statement in the next class.